Hi, this is Group 4. We're working on Homework 4. This is MD Rizwan. I have Alex with me, and I'm sorry to tell you that one of our groupmate, Alexandra, she will not be able to with us because she is having a power outage due to the storm. But we apologize for that. But let's hop on. So this is a linear programming problem involving optimization where Sugarco is trying to maximize profit by deciding how many of each type of candy bar to produce while being limited by available sugar and chocolate. We'll approach this by analyzing the final optimal tableau and using it to answer the given question step by step. So let's see the details of this problem that the three types of candy bars, we use sugar and chocolate, and the following constraints are given. So, so our objective function has become to maximize the profit, which is z equal to 3x1 plus 7x2 plus 5x3. So our constraints are, we have several constraints. The first constraint is sugar constraint, which is x1 plus x2 plus x3, which should be less than 50 because our total sugar available is 50 ounce. Our chocolate constraint is 2x1 plus 3x2 plus x3, which should be less than 100 because our limitation is 100 ounce. And of course, x1, x2, x3 has to be positive number because of the non-negativity of the decision variables. So this is the optimal tableau that we're going to use for to solve our program. So let's focus on problem 1. So in problem 1, we are uh, from the given problem, we start by analyzing the optimal tableau that is provided in table 1, which is here. The optimal solution corresponds to the current basis. To maintain this optimality, when the profit of type 1 candy bar changes, we need to ensure that changes in the profit coefficients do not alter the basic solution. So the objective function, as I mentioned earlier, is equal to 3x1 plus 7x2 plus 5x3. Here, 3 is the profit for type 1 candy bars, like is the coefficient for x1. So now the new profit for type 1 will be if the profit for type 1 candy bars change to C1, we need to ensure that the optimality condition still holds. The reduced cost for X1, the decision variable for type 1 candy bars, should remain non-negative for current solution to stay optimal. So this reduced cost is given by the shadow prices, which is dual variables. So the optimal condition is the reduced cost for X1 must be non-negative. Based on the tableau, for the current basis to remain optimal, the profit of type 1 candy bars must be less than or equal to 6 cents. If the profit for type 1 increases to 7 cents, the reduced cost becomes negative and the current basis is no longer optimal. So the new solution with profit for type 1 equal to 7 cent, that means if the profit for a type 1 candy bar increases to 7 cent, we need to resolve the problem. The new optimal solution will make type 1 candy bars an only product manufactured as they will dominate the production. Thus, the new solution has become uh, new optimal solution will be x1 equal to 50, x2 equal to 0, and x3 equal to 0 with a maximum profit of 350 cents, which is $3.5. So we have also checked our result in the Cplex. So here on the left, we can see the codes. We introduced the decision variables. We have mentioned the objective function to maximize, and we have introduced our constraints. And then on the right, we can see the output. Uh, yeah, sorry. So this was the original function, and this is the solution for our problem A, where we can see our solution. So the solution with objective is 350 cents and x1 is 50, x2, x3 is 0. So let's move on in problem 2. So problem B, here the reduced cost explanation, the reduced cost is the coefficient in row Z for x1 is 3. This is also from Tableau. The meaning that the current objective function coefficient for x1 is 3 cents. So we have to maintaining the optimality for the current basis to remain optimal. The reduced cost must satisfy the condition, which is uh, 0 plus delta 2 should be greater than 0. Then uh, our goal is to determine the range of the value for the profit of type 2 cantilevers, which we mentioned by C2. So within which the current basis remains optimal. The reduced cost for X2 must remain non-negative to maintain the optimality. So from the optimal tableau, the reduced cost for X2 is 0. To maintain the optimality, the new reduced cost must satisfy this 0 plus delta 2 is greater than 0 equation, where delta 2 represents the change in objective function coefficient for X2. So we can set up the condition as it mentioned here, C2 minus 7 should be greater than or equal to negative 2. This is from the reduced cost. So if we simplify that, then we will have an inequality, which is C2 is greater than or equal to 5 and less than or equal to 15. So if that means the profit for type 2 cantilevers must be between 5 cent and less than 15 cent, less than or equal to 50 cent. So if the profit for type 2 cantilever is 13 cent, then we substitute this value into the objective function. Since our C2 is 13, is within the optimal range, which is 5 cent to 15 cent. The current basis remains optimal, meaning the decision variables x1, x2, and x3 will stay the same. So then our total profit will change if we put the value of x1 equal to 0, x2 equal to 50, and x3 equal to 50. I mean, x1 equal to 0, x2 equal to 25, x3 equal to 25. Then our optimal solution will become 450 cents, which is $4.5. So we have also checked this with the Cplex, and this is the result which matches our solution. Now, my teammate Alex will explain problem C. Thank you.
Hello, I'm Alex. I'm going to go over problem C. So for this problem, we were attempting to find what amount of available sugar would the current basis still be optimal. And to find that, you start out with the function where b inverse times b prime, which is trying to find the change in the sugar over the chocolate content. And that turns out to be 1.5, negative 0.5, negative 0.5 matrix times the delta times 100 matrix. And then when you multiply these out, you get two functions. You get two different equalities where you get 50 minus 0.5 delta is greater than 0, which comes out to delta is less than or equal to 100. And the other inequality comes out that delta is greater than or equal to 100 over 3, which is 33.3 repeating. So for the amount of available sugar that would keep the current optimal basis is between the range of 33.3 repeating ounces and 100 ounces of sugar. For the code, we also entered the code into Cplex and Cplex Interactive and found the range constraint for C1, which is the sugar constraint. And this is the range for it, which shows it's 33.3 to 100. For problem D, it asked if there were 60 ounces of sugar available, what would be the new profit? To find this, one way would be to figure out the shadow price of the sugar, which is found by doing CBV times B inverse times delta, which is the following matrices. When you multiply that out with a solver, you eventually get 4, and 4 means that is the sugar shadow price tag. And as it's saying 60 ounces of sugar, that is 10 more than 50, which is the original amount. So you do 4 times 10, which is 40, which means that the price profit increases by 40 cents. So you do 300 plus 40, you get $3.4 as the new profit. And then the next question asks how many of each type of candy bars should be made with this new profit, and that can be given by B inverse times B, which will be equal to the new type 2 and type 3 bars to be made. And then when you multiply those out, you get 40 and 20. So this means that there should be 0 bars of type 1 being made, 20 bars of type 2 being made, and 40 bars of type 3 being made. Then it asks, can a solution be found if 30 ounces of sugars are available? And no, this cannot be found as it is outside the optimal range of 33.3 to 100. So therefore, it cannot be, no optimal solution could be found for this problem. This is also the code. When you enter it in, it shows that if you had 60, it would the optimal value would be x2 is 20 and x3 is 40 and x1 is 0. For problem E, it asked if type 1 candy had 0.5 ounces of sugar and chocolate as its new constraint values. What would the new optimal value be? So this you find by doing CBV times B inverse times A1 minus C1. And once you plug those numbers in, you eventually get it out to that the new you find this this specific equation is trying to figure out if you switch those numbers, whether the solution would be optimal or not. If it's less than or equal to 0, it would not be optimal. So we found that it's negative 0.5, which is less than 0, so it's not optimal, so there needs to be a new optimal solution. Going from there, you try to find out what the new coefficients in x3 and x2 rows, so 0 rows 2, 1, and 2. And you do that by multiplying the inverse of b times a, and then you find out that it's 0.5 and 0. Thus, you get the following initial tableau, and then now you have to solve for x1, entering the basis, and going through all the math in the process of canceling out x1 in the certain rows. So you have to solve x1 for 0 in row 0, x1 for 1 in row 1, and then with that you get the following below tableau. And this means that the new base x1 is now the new basic variable in row 1, so that it means you need to make 50 of type 1 bars, 25 of type 2 bars, and 0 of type 3 bars. And so this would mean that they should start making type 1 bars. Following is the code output showing the same thing I just said, where x1 needs 50 type 1 bars, x2 needs 25, and x3 needs 0. The final problem is adding an entirely new bar to the mix. So we're solving for the new value of x4 in row 0, that is negative, which is given by CBV times B inverse times n prime, which is the new matrix for the values of the non-basic variables. Then you minus that by C NBV prime, which is also adds the new variable. When you do all the math together, you get 3, 4, 1, and negative 1 is less than 0. Since negative 1 is less than 0, that means there is a new optimal solution that needs to be made. To find the coefficients that go into x4 in the tableau, you do B inverse times A4, which is denoted by 3, 4, and the following B inverse. You get that the coefficients should be 2.5 and 0.5. And then the initial tableau is shown below, showing all these numbers put together. Following this, x4 would be entering the basis in row 1, as it is affecting the z constraint the most in that row. Then you'll need to solve for x4 equals 1 in row 1 and x4 equals 0 in row 0 and 2. And then once you solve for that, doing a bunch of basic algebra, the following tableau is shown. Thus, x4 becomes the new basic variable in the optimal solution, showing that it needs 10 bars and 20 type 2 bars to be made. So this means that they should start making type 4 bars if they add those bars into the mix. And the following code also shows that if you did add it, it would also need the same variables that I just said, where x1 and x3 are 0, and x2 is 20 bars, and x4 is 10 bars. That is it for our presentation. Thank you for your time.